Hello, we're going to look at an example of a stoichiometry problem. Specifically, we'll look at an ideal stoichiometry problem, and then we will look at one that deals with limiting reactants. After this, if you'd like more information, feel free to go to the website www.teachandlearnchem.com, where I have many more PowerPoints and many more worksheets for you to use. The compound diborane was at one time considered for use as a rocket fuel. So the question might become, how many grams of liquid oxygen would a rocket have to carry to burn 10 kilograms of diborane completely? Now, I've mentioned that the products of this are B2O3 and H2O. So the first thing we need to do is write a balanced chemical equation. So B2H6 and O2 are the reactants. The product, indicated by what comes after the arrow, in this case, are B2O3 and H2O. This, of course, is the unbalanced chemical equation. We now need to balance the equation. Notice that we have 3 oxygens and a 4th oxygen over here on the product side, and we have only 2 oxygens on the reactant side. So at minimum, we will need to add a coefficient 2 in front of the oxygen. So we can add that 2, and it's a 3 oxygen and 3. Now we have it balanced. All right, moving on. Next, I like to write down the information. Notice that we had 10 kilograms of diborane, and we want to find out how many grams of liquid oxygen we would produce. So we will set this up, setting it up always, what are we looking for? X grams of oxygen equal to, what are we told, 10 kilograms of diborane. The first conversion I put in just to make sure people are paying attention to the units. Notice that this unit is kilogram and the final answer is in grams. So I'm going to go ahead and convert kilograms to grams. And if you recall, there's in 1 kilogram there are 1,000 grams. So by doing this, the unit kilograms and kilograms will cancel just like that. At this point, I now have grams of B2H6, so I have to convert that into moles. So I have to figure out the molar mass of B2H6. Now, what the formula says is I have 2 borons, each that weigh 11 grams, that's 22 grams, and I have 6 hydrogens, each that weigh 1 gram. So 22 grams plus 6 grams gives me the molar mass of diborane to be 28 grams per 1 mole. Notice now that grams of B2H6 cancel just like this. Now, if I were to stop my problem now, my answer would be in moles of B2H6, and I want to get to grams of O2. Anytime I have moles of one substance and I want to go to moles of another substance, I'm going to use the coefficients from the balanced chemical equation. The chemical equation, there's an understood, but although you don't have to write it, 1 in front of B2H6 and a 3 in front of the O2. So I'm going to use those as coefficients, putting the 1 mole of B2H6, that again comes from up here, and then on the top I have 3 moles of O2, that's going to go in the numerator. Notice again now that my units, moles of B2H6, moles of B2H6 can cancel. Now I have, if I were to stop, my answers in moles of oxygen, and I want grams. So I need one more conversion. I have to recall that oxygen weighs 16 grams per mole, but because oxygen is diatomic, that means there's 2 of them, I have to double that number. So 1 mole of O2 has a molar mass of 32 grams. And again, my moles of oxygen cancel, and at this point I just have to type it into my calculator. So I would take 10 times 1,000 times 1 times 3 times 32 equals, divide by 1, divide by 28, divide by 1, divide by 1, and that will equal the final answer, 34,000 grams of oxygen. Let's look at another question related to this. One of the problems with space travel is that when you're stuck in space, sometimes, well, you will exhale carbon dioxide. Let's see what happens here. We see here an astronaut, I believe that's Scott Carpenter, changing the lithium hydroxide scrubber on the space station. Now, the lithium hydroxide scrubber is used to remove carbon dioxide from the air. So as it says in our question, in the space shuttle, the carbon dioxide that the crew exhales is removed from the air by a reaction within canisters of lithium hydroxide. We're told that on average, every astronaut exhales about 20 moles of carbon dioxide per day. And so the question we want to find out is, what volume of water will be produced when this amount of carbon dioxide reacts with an excess of lithium hydroxide? Now, why is it important to make sure you have an excess amount of lithium hydroxide? Well, that's right. You can't roll down the windows in space. You would get sucked out and die. So it's best to bring an excess amount of lithium hydroxide. So I've started by writing the balanced chemical equation showing carbon dioxide reacting with lithium hydroxide to produce lithium carbonate and water. Now, I've taken the question, the 20 moles of carbon dioxide per day, and I've written that underneath my carbon dioxide. I've also noted they have an excess amount of lithium hydroxide, and the question we were asked is what volume of water will be produced? Now, instead of writing X liters, I wrote XG. Can you tell me why? If you said because volume of water to use 1 mole equals 22.4 liters is only at STP, and you maybe knew that standard temperature is 0 Celsius and water is not a gas, you're correct. So what we'll have to do is use the density of water to solve this problem. So as we've done in the past, we're going to set up what are we looking for, X, this case milliliters of water, that's my volume, equal to the 20 moles of carbon dioxide that I have. Now because I have moles of carbon dioxide, I can use the coefficients from the equation. 1 mole of CO2 will produce 1 mole of water. Notice that moles of CO2 is up here, and for that reason moles of CO2 goes down here, so the units will cancel. So again, from the equation, 1 mole of CO2 produces 1 mole of water. Now I'll cancel the moles of carbon dioxide like this. If I stop now, my answer is in moles of water, and I need it to be in milliliters of water. My next step is to use this conversion, 1 mole of water. Now I calculate what it weighs. I have, notice, 2 hydrogens here. They each weigh 1 gram per mole, and I have 1 oxygen. That weighs 16 grams per mole. So 16 grams plus 2 grams gives me a mass of 18 grams. Now I put 22.4 liters in here just because that's what a lot of times my students will do, but we can't do that because, again, as I stated earlier, water is not at STP, so we can't do that. Instead, we have to put the 18 grams per mole, the molar mass of water. At this point, the moles of water cancel above and below, and now we're at grams of water. Now, because we know the density of water, and water has the density, if you recall, of 1 gram per 1 milliliter, notice again the grams of water cancel the grams of water down here. We get our answer 360 milliliters of water. That's how much water you lose a day just by exhaling. That's equivalent to about a can of pop, maybe a little bit more. Now, the next slide I have shows the actual lithium hydroxide scrubbers. If you've ever seen the movie Apollo 13, this is the actual fix they had. They had a round cylinder, and they had to put a square piece in here, and then they used some socks and duct tape, but it was enough to get them home safely. One last problem for fun. Let's pretend that you are going in space. So, according to our question, we want to know. Stop that, Mr. Monkey Business. We want to determine the amount of lithium hydroxide required for a 7-day mission in space for 3 astronauts and 1 happy chimpanzee. And we're going to assume that each exhales 20 moles of CO2 per day. Now we're given a new piece of information here that the lithium hydroxide scrubbers are only 85% efficient. I'll get back to that in just a moment. So my initial step was to figure out how much CO2 is exhaled. So I have 4 passengers, remember 3 astronauts and a chimpanzee. Now, I put 10 days here, even though they're only going for a 7-day mission, because they should plan for a delay just in case they have bad weather in Houston. And so I'm going to estimate I need about 800 moles of CO2 per day taken care of. So we will look, and we go back to our equation we just had, we looked at earlier, and now we want to find out how many grams of lithium hydroxide will I need for 800 moles of CO2. Now I need to get a new sheet of paper, so let me do that. There we go. Now, this is a a mole to gram calculation, so this should take 2 steps. As I've done many times before, I always set them up. What am I looking for? X grams of lithium hydroxide equal to, what do I know, 800 moles of CO2. Now, I'm going to show this in a couple different ways. The first thing I'm going to do, I notice I have 800 moles here. I'm going to use the ratio up here that says 1 mole of CO2 requires 2 moles of lithium hydroxide. So if I have 800 moles here, I would need 1600 moles here, or double the amount, because it's a 1 to 2 ratio. Notice that when I do the math, I get 1600 moles. That is the 1 mole of CO2 going to 2 moles of lithium hydroxide. My next step is to go from moles of lithium hydroxide to grams of lithium hydroxide. And for this, I need to calculate the molar mass of lithium hydroxide. So I've done that, and I find that 1 mole of lithium hydroxide weighs 23.9 grams. So that I've set it up so that my moles of lithium hydroxide cancel. And when I solve that on my calculator, I get an answer of 38,240 grams. Now, if I were the mission specialist and I sent those astronauts in the chimp up with 38,240 grams, they would probably be dead. And here's why. This is an actual yield. That is assuming that all of the molecules react exactly as they should. But in reality, they don't all react. I stated earlier that the lithium hydroxide scrubbers are only 85% efficient. That means you will not get as much as you want. The formula that we use to calculate percent yield, I've shown here. Percent yield is equal to the actual yield, that's what the chemicals do, divided by the theoretical yield. What you calculate when you do a problem on paper is the theoretical yield. So if I were to put some numbers in here, 85% is 0.85. My actual yield, remember, is 38,240 grams. So I can solve for my unknown theoretical yield. And when you do the math here, take x times 0.85, so that's 0.85x equal 38,240. Then divide both sides by 0.85. You will find you would actually need about 45,000 grams of lithium hydroxide to be sure that those astronauts don't asphyxiate themselves. Hey, I've got a lot more problems for you to do. I'm going to stop here. I'll give you some more problems to look at in just a bit.